Welcome back from Thanksgiving. I hope you all had a great break. I'm sure you're trying to get back in the swing of things, and sorry I can't be here with you today. Much rather be there, though, than at the hospital with my son, so I will see you all on Wednesday. Okay, but let's go over. Today we're starting our 5th unit, cubic functions. So we'll cover the attributes of cubic functions today. And in the beginning, we're just going to take a look and see what are some of the things that we want to find out about cubic functions. So we're going to take a look at one to begin with. And yes, do write this down in your journals. I will be looking for this, especially our summary page. Okay, so our first one, let's take a look. Let's say y equals 2x cubed minus 8x squared plus 5x minus 3. So we're going to put that into the calculator and have you take a look at it. Oops, turn it on. So we've got 2x. To get to the cubed, you have to use that little caret button. Raise to the third minus 8x squared plus 5x minus 3. And let's go to the graph. Take a look at what this looks like. Here's our cubic. Ooh, look at that. Comes from down below, comes up, goes back down, comes back up. All cubics will start at one end, either high or low, and finish at the opposite side. So that's going to be something we always see. But let's take a look. What would be possible, the domain of this guy? So what are the possible x values? Well, it looks like when we have negative values, it just keeps going down and down. When we have positive values, it keeps going up and up. So our domain is going to be all real numbers. And remember, domain is all your x values. So our domain is equal to, we can write it as all real numbers. You could also write that with the inequality. So this is the exact same thing. Negative infinity is less than x, which is less than our positive infinity. Both of those mean the same. How about our range? Remember, range is the possible y values. Well, it looks like y's continue to go up and up and up, and our y's over here go down and down and down. So interestingly enough, our range is the same thing. It's all real numbers. I believe this is the first function we've had this year that has the same domain and range. So it goes from negative infinity to y, which is less than positive infinity. Okay, how about x-intercepts? That's always something we want to know. X-intercept. And let's find our y-intercept too when we're at it. Okay, so x-intercept, where does it cross the x-axis? Well, we could do the trace to find it. Does not look like a very exact value. If we go to our table of values, it looks like it's between 3 and 4. Yeah, so at 3 it's at negative 6, at 4 it's at positive 17. So between 3 and 4 it crosses the x-axis, but I want to know an exact value. So to do this, let's go back to our y equals. And under y2, put in the value of 0, which is simply your x-axis. And now if we go back to our graph, it's not very exciting. It doesn't really draw anything, but it has actually drawn a line right here. And we can use the intersect function to find this. So if you do second trace and choose option 5, intersect, let's move our cursor a little bit closer to right there. So using the right arrow, ooh, it's like going on a roller coaster. Put it somewhere close to the intersection point and press enter 3 times. And it comes back and tells us our intersection is at 3.3935, blah, 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 and y equals 0. So our x-intercept is at 3.39, 0. And 2 decimal places are fine there. So x-intercept is at 3.39 and 0. Our y-intercept, that's going to be when x is 0, what is the y value? So we can go to our table of values to find that. So second table, and so when x is 0, y is negative 3. So our y-intercept is at 0, negative 3. Well, that's a lot nicer, isn't it? Okay, we have a new term now with our cubic functions. And any higher order polynomial, so whether to the third power or higher, you may see this term. And it's called a local maximum. And this means where the graph is temporarily at a peak. So if we come back over here, we've said that our domain goes all the way up to the range goes all the way to infinity, but there's a peak right here, if you notice. So we want to find what are the coordinates of that. Oh, it's almost like a vertex, isn't it? We want to see what, in this little area, what is that peak or that maximum. And to do that, we do second, trace, and it's a maximum we're looking for, so we choose option 4. And to find it, calculator is asking you for the left bound. So you need to move your cursor to the left side of the maximum. So again, we just back up over the maximum and then slightly below it. It doesn't matter how far below it you are, as long as you are below it. So you press enter once, and now it asks you for right bound. So we need to be on the right side of the maximum. So there we go. We're on the right hand side. Press enter, and it'll ask you to guess. I don't want to guess. I just want the calculator to tell me the value. So press enter. And it takes it a moment. It has to calculate here. So this tells us the maximum occurs when x is at 0.36 and y is at negative 2.14. So again, we call this our local maximum. So it's at 0.36. I'm going to put that as 0.36 so it's easy to read. And the maximum was at y equals negative 2.14. So we have a local maximum. It's not the maximum of the function. That would be called the absolute maximum, which is at positive infinity. But just the local maximum in that little area. The second term is local minimum. Where does that occur? And like the local max, it's where there's a dip. And we can see this dip right here. Looks like there's one right there. So again, we're going to go to second, trace, but this time we want the minimum, so option 3. We put the cursor, it says left bound, so it's got to be on the left side of the dip. So it's on the left side. We press enter. And now the right side, so the right side of the minimum. So the dip is down here, the minimum. So I'm on the right hand side, I'll press enter. And again, it asks me to guess. I'm not going to guess, I'm just going to press enter. And it's thinking. And it comes back and tells us what that point is where we have a local minimum. And we're going to write that down. Our minimum occurs at x equal to 2.3, and remember we have to round up. So the 5 would force that 0 to round to a 1, so 2.31. The minimum, the y value is at negative 9.4, and again the 8 is going to round to a 9 because it's followed by a 6, so negative 9.49. So now, so far on this function of cubic, we've had a domain, range, x-intercept, y-intercept. We have a local max, a local minimum, and there's something else on this that's called our ending behavior. So let's write that down. Ending behavior. That is, what is the y value when x gets really, really big, and what is the y value when x gets very, very small? So when x is getting big, we say x approaches infinity. So think of this means approaches. So when x approaches infinity, what is the y doing? Well, if we look at this, we said it just keeps going up to infinity. So as x gets bigger, y is also getting bigger. So y approaches infinity. If x approaches infinity, y approaches infinity. Likewise, we want to know in the opposite direction when x approaches negative infinity. So as x approaches negative infinity, x gets smaller and smaller. What is y doing? And if we look back on our graph, we said that y just keeps getting smaller and smaller and smaller, right? If I went and zoomed out on this guy, let's see, zoom out, just so you can see a little bit better. Well, it's hard to see. So it came up, went down, went up. So as y gets smaller, it's just shooting down here. So as x gets closer to negative infinity, y is getting closer to negative infinity. So those are some of the things we're going to be looking for on cubes. We're going to look for domain and range, x and y intercepts, local max and local min. They won't all have these. also we'll be looking at our end behavior. What happens when x approaches infinity? What does y do? Or what does y do? And as x approaches negative infinity, what is y doing? Okay, so let's take a look at our parent function. Okay, so our parent function, so this is going to be our cubic parent function, is y equals x to the third. So to make this the simplest cubic there is, it has to have an x raised to a third power. It can have smaller terms, x squared, x, and constants, but it has to always have this piece to make it a cubic. So let's take a look at our parent function here. Okay, so we're going to go back to y equals, and oops, what did I do there? Come on, calculator. Mine is stuck thinking. Great. Okay, so let's plug in y equals x to the third power into your y and graph it. Take a look at what it looks like. And you'll probably see, oops, goodness, x raised to the third power. It doesn't quite look the same as the previous one we looked at. It starts from down low, comes up, looks like it goes to the origin, and then continues up. What's missing though? What did we see on the other one that we don't see here? Let's just leave that for a moment while we look at our domain and range. Domain and range. Now our domain, again, it looks like we can keep going out. X can get smaller, x can get bigger. It still will occur. So our domain on this is all real numbers. So I'm just going to use the fancy R for all real numbers. My range, again, it looks like it gets smaller and smaller and bigger, so my range is also all real numbers. How about our x-intercept and y-intercept? Remember, for our x-intercept, we have to go back to y equals and put in the value of 0 for y. And go to our graph. Even though it looks like we know what it is, let's double check. Second, trace, option 5, and press enter 3 times. 1, 2, 3. And sure enough, it does tell us. It goes right through our origin, so that's both our x-intercept and our y-intercept. 0, 0, 0, 0. Okay, how about local max and local min? So local max, local min. Does it look like we have one? And this is the unique thing about our parent function. It does not have a local max or a local min. So we'll just put none down. And the last thing we want to know is our ending behavior. Ending behavior. Okay, so that means when x approaches positive infinity, what is y doing? So if we take a look, as x gets bigger and bigger, y is continuing to get bigger and bigger. So we'll just write, as x approaches infinity, y approaches infinity. And that's positive infinity in both cases. As x approaches negative infinity, so as x goes further and further out, what is the y value doing? And it looks like it's just getting smaller and smaller. So y is approaching negative infinity. So those seem to go hand in hand together. Let's take a look at a third example now. Okay, this one's going to be a little bit different. So if you want to label this as example 3, feel free to. So this one, let's look at y is equal to negative x cubed plus 7x squared. Okay, and I don't want to put the negative in parentheses. So when we go to our y equals, we're going to put in negative x, oops, I should have cleared that, negative x raised to the third power. And my calculator is a little different in how it shows it. Yours will have the caret there. Plus 7x squared. And I'm going to leave y2 equal to 0 because I know I'm going to want to find my x and y intercepts, so I might as well leave that in there. Let's take a look at our graph. Ooh, so it's come down, it's gone up, but then it comes back down. And it's gone up so far that I can't see it. Okay, so I'm going to have to take a look and change my window. Let's go ahead and just try zooming out. So if I go to zoom, option 3 out. Ooh, I still don't see it. Okay, I'm going to adjust my window. Or let's try zoom fit. Zoom, option 0. Let's see what this looks like if it... That did not show us at all. Okay, back to our window. So I'm going to go from negative 10 in x. And I think we can still stay with positive 10. It's the y value we need to adjust. I do not want to go to negative 52,000. That's way too... Let's go from negative 50, how about? And up to a positive 100. And let's take a look at what it does. Okay, there we go. We can see it a little bit better. So it does that same thing. It comes down, goes back up, and comes down. So this time, it starts at the top and finishes at the bottom. Our domain is still all real numbers because it looks like when we keep going x smaller, it exists, and when x gets bigger, it exists. Our range is all real numbers. Okay, x-intercept. Where does it cross the x-axis? Okay, so again, to do this, we have to go to second trace. We're looking for intersect. So it looks like it's over here. So I'm going to press enter 3 times. 1, 2, 3. And it says our intersection is at x equal to 7 and y equal to 0. Oh, over here it says, Okay, so we have an intersection at 7, 0, but it didn't find this as an intersection at the origin. Let's take a look at our table and just see. It does go through there though, doesn't it? Well, it doesn't go through, it touches there, but it doesn't go through. So this is still an x-intercept at 0, 0, but what we call this is that it bounces there. Oops, let's put it so you can see it. So it comes down, it bounces at 0, 0, and goes back up. But for our purposes, we do call that an x-intercept also. So we have 2 x-intercepts, 0, 0, and 7, 0. Our y-intercept, I don't need to go to the table to look, because I already know that it's at 0, 0. So y-intercept is at 0, 0. Okay, it looks like we do have a local max and a local minimum, so we're going to take a look at those. So local max. Remember, to find this, we have to go to second trace. We're going to choose max, so option 4, and we need to be on the left side of the maximum. So using your left arrow, just move along till you're to the left of that maximum. Press enter. Move to the right side now of the maximum, because that's what we're trying to find, and press enter, and then enter again. And it will come back with a value for us. And we're going to have to round this one, it looks like. So this is going to round to 4.67. The y value of 50.81. And make sure you're getting comfortable at having the calculator do these, because you will have to do this on homework or on quiz or on a test. So local min. Again, we're going to go to second trace and tell it we want the minimum. So option 3. And we have to go to the left side of the minimum. So I need to move my cursor along this curve using the left arrow. Till I'm over on the left hand side. And again, it doesn't matter where you are to the left, as long as you're to the left of the minimum. Press enter. Now go to the right side using your arrow key till you're to the right of the minimum. Press enter and enter again. So notice, remember these e's. If it's e to the negative power, we just count that as 0 because it's a slight calculator error. It's not calculating that that was 0, 0. We actually already knew that because that was our y-intercept and x-intercept. So our local min is at 0, 0. Our local max is at 4.67 and 50.81. Notice these are not nice numbers. That's going to happen with cubes. Okay, last thing we want to find on this guy is our ending behavior. So as x approaches infinity, so as x gets bigger, what is y doing? Ooh, look at that. Y is getting smaller as x gets bigger, correct? So y approaches negative infinity as x approaches positive infinity. The second thing we always want to look at is as x approaches a negative infinity. So as x gets smaller and smaller, what is y doing? Look at that. It's getting bigger and bigger. So y approaches positive infinity. And no, you don't have to write the positive there. I just wanted to emphasize that they're going in the opposite direction here. So x is approaching negative infinity, y is approaching positive infinity. Okay, that sums up the third example. One last example, and then we will move on. Okay, so example 4. Y equals x to the third plus 5x squared minus 2. And let's reset your calculators because we did some zooming on that last one. So second plus 712, just have everything back to normal. And let's plug in this guy. So x to the third power plus 5x squared minus 2. And we want to, again, put in for y2, let's put in the 0 because we'll have to find our x-intercepts on this one. And let's graph it. Nope, it went off again. Okay, so this went a little bit higher. It looks like it came back down and then goes back up. I'm going to just go to my window to change it because it looks like I don't need to go much higher in y. So let's just modify that by going to window. And I'm going to leave the x and y alone. But my y max, let's go up to 20. And I'm pretty sure that's going to give us the whole picture. Yes, there we go. So it comes up, goes down across the x-axis and back up across the x-axis. Okay, so domain. What does it look like? All real numbers again. And our range is all real numbers. So we can keep going to smaller and smaller x's and bigger x's. Everything still works. Okay, x-intercepts. Just looking at this, how many x-intercepts are we going to have? We have one here, and one here. So there's going to be 3 unique x-intercepts on this cubic function, which is the most you'll ever have on a cubic function. And again, to find this with second, trace, we're going to choose option 5, intersect. Here's where my cursor is. I like to go in order to make sure I find all of them. So I'm going to move my cursor all the way over to the left using that left arrow. Up and over that maximum. Back down. And so now I'm close to this intersection. And I'm going to press enter 3 times once I have it in the correct spot. 1, 2, 3. And it gives us our x-intercept is at negative 4.92 and y is 0. Okay, if I want to find the second x-intercept, which I do, I'm going to have to go back to second, trace, option 5 again, and now I need to move the cursor close to the intersection point I want, which is over here. Using the right arrow, go up and over the maximum, and come back down close to this intersection point. That looks like it's close enough, and press enter 3 times. 1, 2, 3. So this intersection is at x equals negative 0.68, and of course y has to be 0 if it's an x-intercept. Okay, and let's find our third x-intercept. So second, trace, we want option 5, And now I need to move the cursor closer to that last intersection point. I'm a little bit above it, but that's okay. I'm still closest to that one. And press enter 3 times. 1, 2, 3. So again, we have to round this. So 0.59 is going to round up to 0.60. So 0.60, comma, 0. Those are my x-intercepts. Okay, that was a lot. Y-intercept. How did we find our y-intercept? Remember, on this one, we just go to our table. So second graph gets us to our table, and we want to see what is the y value when x is 0. So when x is 0, under y1, it is at -2. So our y-intercept is at 0, -2. Okay, so we've gotten our domain, range, x-intercept, y-intercepts. Last thing we need is our ending behavior. So again, this means when x approaches in positive infinity. So as x is getting bigger and bigger, what is y doing? Well, we can look at our table to find this as well as our graph. As x gets bigger, what's happening to our y values? Look at those. They're getting much, much bigger. So y is approaching positive infinity as x approaches positive infinity. As x approaches negative infinity, so as x gets smaller, let's take a look. What happens to our y values? Smaller, smaller. Notice they start to get bigger again. I'm just moving my key here, the up arrow, to take a look. And once we get past that local maximum, they start getting smaller and smaller and smaller. So again, we saw this on the graph. As x gets smaller, y gets smaller. So y approaches negative infinity. Okay, so we've got all of our characteristics now summed up for this cubic function. Okay, you do have homework tonight. First, though, we want to take a quick review of some quadratics.